This is a supplementary lecture for FEEG 1003 thermofluids, and it concerns dimensional analysis and its sort of application and relevance to civil engineering. So dimensional analysis has two main sort of uses. The first one is for scaling hydraulic or fluid problems. And I say hydraulic, actually it can apply to many other things as well, mechanical, not necessarily just hydraulics. But we can use it for scaling, and scaling is very important in terms of, in civil engineering, 95% of what we do could be design and construction of very unique structures, sort of one-offs. You know, there's only, obviously, if you look at iconic buildings, you don't really see them replicated any time. So, you know, so the Mio Viaduct, for example, each one of the bridge piers is individually unique, different heights, and there's only one bridge of that design anywhere in the world. So when it comes to designing it and testing it, we can't afford to test at full scale. We can't build multiple versions and choose the one that doesn't fall down. So we have to do work at smaller scale. So you'll see civil engineers using, for example, doing tests in heavy structure labs on strong floors, strong walls, in wind tunnels, in water channels and flumes, and then scaling the results up to infer something for the full-scale system. So by way of an example, this is my research, which one of my areas of research, which is marine renewable energy. So these are tidal turbines, and these work just extracting the kinetic energy of the moving fluid. So literally, I guess, analogous to underwater wind turbines. My version is on the right-hand side, probably quite obviously. Costs about £50,000 in terms of design and development, and we keep incrementally upgrading it. It's 0.8 meters diameter, and we can test that in a channel, or indoor water channel, for about €20,000 per week. The one on the left is a full-scale prototype. This costs between £6 and £8 million and is 16 meters in diameter. And I can do testing on my model version and then infer the results up to the full scale. So for example, both of these rotors have very similar power capture sort of efficiency. It's called the coefficient of power. On my blades, it's about 0.44, and it'll be similar for the one on the left. So if I was to, I could potentially recreate their blades, scale them down, and then test them on a small version. So again, the testing we can do is very controlled environment, very precise, and very cheap compared to building multiple large systems. So the second use for dimensional analysis is a bit more fundamental. It's used for ascertaining what variables are important in a particular problem. So to give you an example, there's a way using one of the various means of dimensional analysis to derive an equation for the volumetric discharge over a weir in a river. You can do it that way, or you could also do it by applying the conservation of energy. But with dimensional analysis, if you think carefully about the variables that are important, you can actually use it to derive equations. Some of these have already been done. So some various non-dimensional numbers like the Froude number, the Mach number, the Reynolds number. Again, all sort of came into existence back in the day when if you found something out, you could put your name after it. And these are quite common, but there are other, you know, every sort of engineering problem is reasonably unique. So quite often you might need to use dimensional analysis to work out relationships. So a quick overview of dimensions and units. Dimension is a fundamental property. So the key ones in terms of this module are mass, length and time. We don't really use temperature. And a unit is what we use to quantify one of these dimensions. So obviously for length, we have the SI unit, which is the meter, but there's obviously various others, the foot, the inch, kilometer, the mile, etc. And the same for velocity and everything else. So we've got three different types of sort of dimension type groups. We've got the geometric, which is just a function of length. So length, area, volume, second moment of area, for example. Kinematic properties, independent of mass, but do include time. So time, velocity, volumetric discharge, etc. And then finally, dynamic, which all are a property of mass term. So there must be a mass term in there. If you look at the list, they're all divisible by mass length times to the -2, which is the fundamental dimensions of force. So if you divide through by that, you can see what the relationship of everything else is to force. So you can see that energy is force times distance, power is force times velocity, for example. So it's very useful to remember some of these key dimensions of these parameters. So here's some examples now. This is a hydraulic model of a dam in India, and you can see the full-scale dam as it was constructed on the bottom right of the screen, and you can see the reasonably substantial hydraulic model. Now the flow in this is really complicated, and we can't always use computational fluid dynamics, which is a common sort of tool in this area of civil engineering. If the flow field becomes too complex, the numerical models break down, and it's very difficult to have a lot of faith in the answer. They obviously look very nice, but they can be overstretched. So a couple of years ago, there was a Formula One team. I think it was a Toyota team. And this is going back a little while now, but they did very, very little or couldn't afford to use wind tunnel testing. So they did it all computationally, and obviously it's much cheaper just to buy 10 or 20 high performance computers. So they ran all their simulations numerically. What they did, they under predicted the drag of the chassis or the general car. So actually when it came to early season testing, they found out the drag was much higher, therefore their fuel consumption was higher, and they'd undersized their fuel tanks. So for the first 5 or 6 races of the season, the team had to retire before the end of each race because they were running out of fuel. So again, had they done wind tunnel testing with a scale model, or even you can even fit a full scale car in some wind tunnels, they would have found this out. So over-reliance on numerical models. Again, this is the Three Gorges Dam, so this is in China. And again, if you look at the aerial shot of the reservoir, you can see it's incredibly complex. It would take such intensive computational resource to mesh that. And meshing is whereby you create the geometry of the problem or the structure. Incredibly complex. You'd have to really simplify it, and there's an awful lot going on. So again, very, very difficult to model that accurately with a computer. Breakwaters, again, we don't really want to have breakwaters failing. We don't want to do our testing at large scale. Also, with any sort of structure that interacts with the sea and the waves, we might have to wait a very long time for specific types of wave to hit this breakwater in real life. Obviously, when we do scale testing, we can, with a wave maker in a towing tank or a wave basin, we can generate multiple different types of wave on demand. So we can test very, very quickly over a range of sea states the integrity of these structures. So experimental testing is very useful, and obviously we'd have to scale then the wave height, frequency, different types of spectra, so different groups of different types of waves we could fire at the breakwater. So all that could be scaled down, and then we'd geometrically scale the breakwater down. And then what we would scale back up again is the forces acting on the structure. So we do testing of a small model in a wave basin and then scale that up to a full 100-meter breakwater that's 6 meters high, for example. This was a good one. So this was that's the Palm in Dubai. There was no hydraulic model made of this, and it was a great program on Discovery Channel. Effectively, what happened was you have these regions just in here at the base of the leaves, and when they constructed it, they realized there was very little circulation. They'd modeled it numerically, and the numerical model had showed water circulating all around the palm. and that basically keeps the water fresh and stops it from stagnating. Well, when they started construction, they realized that wasn't the case. The numerical model was wrong, and they were getting algal blooms and all kinds of nasty stuff inside the palm. And obviously, this is a very expensive build designed for very rich people, so they didn't really like the smell. So what they had to do was cut large sections out of the outer part of the structure. So they created all these gaps to allow water to come in and circulate around. At the time, they said it was very novel and they solved a really interesting problem. However, the problem arose because they didn't do any scale testing. They just relied on numerical model. Top right, this is Poole Harbour along the south coast in the UK. This is the largest natural harbour in the world. And again, imagine trying to model that with a computer. It's all the complex geometries and all the islands, very difficult. We can use it for sediment transport and flooding. Again, you don't want to have to flood a real thing, so it's a lot easier to scale it down in a model and then test what happens when we have the 1 in 200 year flood, for example, 1 in 200 year flow down a river. And we can also scale sediment down and look at sediment transport and sediment modeling as well. That is notoriously difficult, actually, sediment transport, to do numerically anyway. So quite often experiments are the best way forward, just because there's so much going on, such complex physics. So let's look at some models. So we can have a geometric sort of type of similarity. So it means a similar sort of shape or dimension should exist between the prototype, the big thing, and the model, which is our small thing. So we can scale up geometrically. So a unit of length in the model is equivalent to X units of length in the prototype. So we're all familiar with geometric scaling, so 1 to 50, things like maps. So all the lengths in the model are 50 times smaller than the prototype. Kinematic, same thing, but this relates to motion, so it could be a velocity type ratio. And then dynamic, this is the scaling of forces. So 1 Newton force in the model is equal to 10 Newton force in the prototype, for example. So there's different types of scaling parameter. Some of these you might have heard of. Obviously Reynolds number you looked at in lab class 1 on this module. So that's the ratio of inertial to viscous forces of a fluid. The Froude number, that's relevant to open channel or gravity-driven flows. The Mach number, again, you should be all aware of that one, even being not being aeronautical engineers. Mach number is relative to the speed of sound. Weber number for surface tension, that can be important in hydraulic models if we scale them down geometrically and they become very large, so very large area but very, very shallow. And there are various others as well that have their own individual sort of unique names. So in my work with the tidal turbines, I have to scale both the channel, so the kind of the water channel they're in, but also the flow across the devices, and they're underwater. So I have to use the Froude number and the Reynolds number as two of my main scaling tools. So what we're saying is that we're going to try and keep the same Froude number. So this dimensionless ratio, we're going to try and keep that the same in the model and in the prototype. Now you can see the equation Froude number written out here in full on the top left. So the velocity in the model divided by square root of g in the model and length in the model will be equal to the same ratio in the prototype. Now, gravity is going to be the same, assuming that we are doing all of our experiments on planet Earth and we're not moving to the moon for anything. And we're also not accelerating our model to our scale water channel vertically upwards or vertically downwards. So we can say that gravity is the same. So we end up with a velocity ratio, and that's equal to the square root of the length ratio. So here we go. So this is the open hydro turbine at EMEC, the European Marine Energy Centre, up in the north of Scotland. That's in a real channel, and that real channel is running at 3 meters per second and is 30 meters deep. So when that turbine goes underwater and gets submerged, the flow will interact around the structure in a certain way. So I need to scale that down to my water channel, which is well, considerably smaller. So I need the same sort of type of flow regime effectively. So what we're saying is the velocity ratio is equal to the root of the length ratio, and we've got some numbers in here. So what we can write out, I'll try and do this neatly in pen, but it probably won't work. So what we're saying is the velocity ratio equals the square root of the length ratio. So we've got velocity in the prototype divided by velocity in the model. That was excellent handwriting. Is equal to the square root of length in the prototype. Oops. Length in the model. Okay, so Vp over Vm is going to be equal to 10 because we've got the length in the prototype, which is 30, divided by 0.3. Oh no, hang on, what are we trying to find? We've got to ascertain the depth. Okay. Well, anyway, I've skipped a stage here. So what we so if we work all this through, plug in the numbers. So the length in this channel here, so the flow depth is going to be 0.3 meters. Okay, at 0.3 meters depth and 0.3 meters per second will give us the same flow conditions as this channel, which is 30 meters deep, running at 3 meters per second. Okay, so I can scale the type of flow down. Okay, this is my other problem in my line of research. When it comes to flow over the turbine blades, we need to scale using the Reynolds number. So we need the same Reynolds number across the blades in order to get similar flow. So now we've gone from looking at the whole channel to a smaller part. And again, Reynolds scaling is very important when you go into wind tunnels for aircraft, Formula One, any other application really. So here now we've done exactly the same. We've taken parity between the two Reynolds numbers. So the big Reynolds number, or the Reynolds number of the big thing, is going to be equal to the Reynolds number of the little thing. Obviously, some of these properties, if we use the same fluid, the density and the viscosity will be constant. So we end up with a ratio, again, just a function of velocity and length. And it's down here. So the velocity ratio is equal to the length ratio to the power of -1. Okay, so here's another problem that I have to face. So the Reynolds number across full-scale device might be approximately about 1 times 10 to the 6, so almost a million, which is not uncommon. You get similar numbers for wind turbines. So we're saying the tip of the blades on a full-scale tidal turbine have a chord length of 0.5 meter, and the tip speed will be 10 meters per second. Now my blades, the chord length, so the sort of the width of the blade at the tip is 20 millimeters. So I've got to work out to keep the same Reynolds number, so the same flow conditions over the blade, how quickly will my blades have to move? So how quickly will I have to rotate my turbine? Now, again, so the length ratio, velocity ratio is equal to the inverse length ratio. So we've got the velocity in the prototype divided by velocity in the model. Oops, terrible handwriting. Equals the length in the model over length in the prototype. Okay, if you plug the numbers in to keep the same Reynolds number across my smaller blades, they have to rotate at 250 meters per second. Okay, not only would that be impossible, I'd have to actually power the turbine to get it spinning that quickly, because the blades can't generate enough lift force to turn that fast. Also, at 250 meters per second, that it would just literally be a blur. So it would appear to the fluid almost as a solid disc, not as a rotating set of 3 blades. So it's just clearly not possible to scale the Froude number and the Reynolds number together. Again, because the velocity ratios or the length ratios are not the same. So velocity ratio is a square root of length ratio, and here it's the inverse of the length ratio. So what do I do? Well, I could run the channel faster, much faster, in order to try and get the blade spinning more quickly. Once I start doing that, we have an interesting problem in that the Froude number is sort of analogous to the Mach number. So the conditions of the flow, when it's greater than 1 or less, or the Froude number is less than 1, gives us two completely different types of flow, called subcritical and supercritical. And you'll study this in part 2 hydraulics. So I can't do that, because if I did that, the channel would behave in completely the wrong kind of way, and I wouldn't be simulating the same type of flow. So what we have to do is basically scale the Froude number, so keep parity of that, and take a hit on the Reynolds number. So the Reynolds number across the blades is what it is. We can try and make the rotor spin a bit quicker, and we can obviously make the blades a bit thicker, or a bit wider, sorry, to try and increase that Reynolds number. So when we do our tests, our Reynolds numbers are about 1 × 10⁵. So it's an order of magnitude lower than the full scale. However, from lab class 1, when you looked at Reynolds number, you worked out that, or you were told that for flow in pipes, the turbulent Reynolds number is about 4,000. So anything above 4,000 and the flow is fully turbulent. So luckily, the Reynolds number over our blade still gives us a turbulent flow. And actually, the efficiency of my small turbine is very similar to the large turbine. So we're confident that we can recreate, even at a slightly lower Reynolds number, it's still within that turbulent classification. So actually we can do a lot of work at this small scale with the same Froude number and infer results up. So it's quite useful. Okay, moving on. We're now going to look at Buckingham PI theory, which is a kind of a method, really, of how to do dimensional analysis. There's various others. There's the Rayleigh method, for example. But we're going to use Buckingham PI. It's fairly comprehensive. It's very procedural. So you have to follow the steps very carefully and precisely, and you will get the right answer. But you just have to do it in the way that it's designed to be used. That's all I can really say about it. I don't know why it's called Buckingham PI. If you can't sleep one night, maybe look it up on the internet. So it's a more elaborate way of doing dimensional analysis, but it's very robust. And what it states is that we have a collection of variables of number n, and they contain a number of fundamental dimensions m. We can rearrange all of those quantities into n minus m independent dimensionless groups. So for example, we have 5 parameters and they contain 3 fundamental dimensions, mass, length and time. We can arrange those 5 variables into 2 groups. And what we do is we use law of indices to put some of those, so we have 2 groups, we'll take 2 different sets of those n variables and raise them all to certain powers, and then we will rearrange or equate the indices such that the indice for length, mass and time is equal to 0. So it's got no dimensions. So we can do all this and we will end up with an equation, for example. If we're doing, say, equating the trying to work out the flow over discharge over a weir in a river, we can work out the equation we need to use to quantify that. But this is only dimensional analysis only deals with fundamental dimensions. So we will receive a set of variables out that could be the answer. However, it doesn't determine any sort of constants. So if you have to multiply the number by 0.86, for example, that has to be done by experiment. So a good example is flow over a weir. There's different designs of weir. The same fundamental equation is used. However, there's different coefficients based on the shape and construction of the weir. And those coefficients are determined by experiment. So usually, if you're hitting a problem completely fresh, you've got to have a good first guess what variables might be involved. This is really down to experience and engineering judgment. But most of the questions you'll encounter, the variables are already defined for you, and you'll be told what they are. So there's part of dimensional analysis where we have to choose some variables to fix. So if we've got two dimensionless groups, we will have some variables that are going to appear in in two groups, in both groups. These are called repeating variables, and we'll have some fixed variables, and they appear once in each pi group. I'll go through an example on the board in a moment to make it fully clear. Okay, but that's so choosing the repeating variables. If we get it right and choose the correct ones, we will come out with a very, very quick and simple solution. Buckingham PI will take half the time, and we'll get very nice outputs. If we choose the wrong ones, we can still get to the right answer, but it's far harder work. We might actually have to modify the dimensions groups at the end, sort of like post-process them to get them into a more manageable and easy to use form. So you'd still get the right answer regardless of if you choose the correct repeating variables or not. But if you choose the right ones, you can make Buckingham PI very sort of far more quick and easy to apply. So there's some guidance or some rules for choosing repeating variables. They can't form a dimensionless group on their own, because if they do, then we'll find that our group of our pi groups will have some dimension once we've done the analysis. So that's not particularly helpful. So the repeating variables don't have to appear in all pi groups. We put them in each time, but sometimes the Buckingham PI process or method means that some of them disappear. So actually the parameters or the variables are raised to the power of 0 and they disappear out of the final equation, which is fine. That does happen. And finally, the repeating variable should be something that's nice and easy to measure by experiment. So for example, I think I've written there, so fluid depth is more useful than, say, the height of any riverbed roughness, for example, which might be more difficult to quantify. Velocity is another easy one to measure, and things like maybe density or something with a mass term that's fairly simple. Try and avoid I guess try and also specify easy to measure, but also the most basic. So I showed you those groups before of geometric, kinematic, and dynamic properties. And if you choose the ones towards the top of those lists, so things like length, velocity, mass or density, they tend to work quite well. So this is our problem. And this is again an application of Buckingham PI to a real problem, and the equations that come out are real dimensionless groups. So in turbulent flow, the head loss, which is the kind of equivalent to the energy loss when a liquid flows through a smooth pipe, is dependent on the following quantities. We've got 6 there. Okay. To form it says determine the form of the equation, and we're going to use V, so velocity, diameter, and density as our repeating variables. Okay, so we've got six parameters. One of them is already dimensionless, the head loss. So this is the energy loss per unit length of the pipe, and this way energy is measured in meters, which I won't get into now. It's obviously not truly energy because it's got the units of meters and dimensions of length, but it's equivalent to the energy loss. But that's length divided by length, so that's already dimensionless. So we've effectively got 5 left. So velocity, diameter, density, viscosity, and acceleration due to gravity. And you can see that in those 5, we've got length, time, and mass. So we've got 3 fundamental dimensions. So that means we can arrange those 5 parameters into 2 dimensionless groups. Okay, so we'll go over to the board now, and I'll run you through Buckingham PI. And then we're going to repeat the exercise, but for a slightly different set of repeating variables. And you'll see that the Buckingham PI analysis becomes a little more difficult to do second time round.
Right, I've written the problem out here. So we've got our head loss, h over h. It's some function of these variables. Okay, we've already determined that we've got five parameters here, and they incorporate three fundamental dimensions: mass, length, and time. So we're going to arrange them into two groups. And the way Buckingham PI works is that for these two groups, we're going to have one parameter or one variable that only appears in one of the groups, and then all the others are going to repeat. So they'll appear in all of the groups. So what we're going to do is velocity, diameter, and density, nice and easy to measure. They're going to repeat, which means that the dynamic viscosity and acceleration due to gravity are going to appear in one group each. Okay? So for our first pi group, so pi 1 is going to be equal to velocity, diameter, density, and dynamic viscosity. The second pi group will be v, d, rho, and then acceleration due to gravity. So these variables only appear, I say, in one pi group only. Okay. So the next stage. So now we've set this up. Oh. Pi 2 is going to be v, d, rho, g. The next stage is to write out the fundamental dimensions of each one. And just before we do that, what we also do in Buckingham PI is we raise all of the repeating variables only to some power. So in our pi 1 group, I'll call this A1, B1, C1. We leave the fixed variable alone. Okay? So the pi 2 group, you can use different numbers and different letters if you want, it doesn't really matter. A2, B2 and C2. Okay, probably a bit too small to read. Okay, so this is just the way we do it in order to get a dimensionless group. Right, next thing we do is to write out the fundamental dimensions of all of this stuff. And this is where you have to obviously use your engineering knowledge and just take a bit of care. So our pi 1 group, we have velocity, which is length times the minus 1. And we raise that to the power of A1. Diameter is just length, power of B1. Density is mass per unit volume, so mass length to the minus 3 to the power of C1, and then viscosity, which I always forget to remember, is mass length to the minus 1 times the minus 1. Okay, so we've written all this out. Now what we're going to do is equate each one of these powers to 0. Okay, we're going to, so not the powers, we're going to equate all of each fundamental dimension to the power of 0. So this is where you've got to be a little bit careful. So we'll do it first for length. So what we're going to say is the power of length effectively is going to be 0. So 0 equals all of the length terms, okay? So now we go through very carefully and look at what is raised, which length terms are raised to the powers. So we have L here, so 0 equals A1. We've got length to the B1 here, so plus B1. There's a minus 3 here, so minus 3c1, and then we have a length term at the very end here, so minus 1. Length's usually the hardest one to do. It's easiest to do mass and time most often. So do the same for time. Again, so the exponent of time, or the power we raise it to is 0. So we have minus 1 here, so minus 1a, or sorry, minus a, 1. And any more t's, 1 at the very end, minus 1. And finally for mass. Again, usually the length terms are quite numerous, so it makes more sense to solve for mass and time first, usually. So 0 equals 1 there, so C1, and then an M here, plus 1. Okay, and now we can solve for A1, B1, and C1. Okay? So if we solve those, we end up with each one is equal to minus 1. Okay? So we can also scrub those out. Okay, so remember we have velocity, diameter, density, and viscosity. Okay? These 3 to the power minus 1, that one's been left alone. So our fundamental dimensionless group is equal to that, which may look familiar. We call it pi1 group. Okay, so we've got dynamic viscosity divided by this term here. If we put all the dimensions back in, they'll all cancel out. Okay, because we've done it properly. Now, the interesting thing with dimensionless groups in Buckingham PI is that you can manipulate the groups to a certain extent. So you can probably see that is the inverse of the Reynolds number. Okay, because the dimensions in the numerator and denominator are identical, we can flip it around. Okay, if you ask me for a unit of length on a construction site, and I said it was 1 divided by 43 meters, you think I was very strange and awkward. Okay, so this is effectively 1 over the Reynolds number, which is not of great use, but we can invert that quite easily. Okay, what we can also do with dimensionless groups is combine them together, because as long as you're careful, you're multiplying or dividing a dimensionless group with another dimensionless group. And we can sometimes use this to detangle the outputs of Buckingham PI, especially if we've chosen the slightly different repeating variables. And then we can come up with these dimensionless groups that we're familiar with, things like the Mach number, Reynolds number, the Froude number, for example. Okay, so that's our first dimensionless group, which is Reynolds number. And now we need to do exactly the same again, and I'll go through it again on the board for this second group. Right, so this group now here, we've got velocity, so I could have actually kept that on the board, couldn't I? Length times minus 1. This times the power of a, call it A2, length to B2, mass length to minus 3 to C2, and then acceleration due to gravity, which is length times to minus 2. Okay, so equating for length, again, same process, 0 equals A2 plus B2 minus 3 C2, and then 1 on the end, plus 1. Time, so minus A1 minus 2 at the end, and then for mass, we've got the 1 mass term here, C2, haven't we? Okay, so equating those, clearly You'll see that our mass term's disappeared now. Sorry, computer went to sleep. So the mass term's disappeared. So C2 is obviously equal to 0. That means that the one term with any mass in it, density, has disappeared from our fundamental group. Which again, we've done this correctly, so there's no problem with that. But that's, as I said before, sometimes the repeating variables do disappear. And that's the case this time. So C2 equals 0, so that's gone. And then A2 is minus 2, and B2 equals 1. Okay, so we can put that back into the equation. So effectively the density, I shall do it up here. So the second pi group, so we've got B2, so we've got our diameter up there. Same with G, and then, find that. Even with a sign on the door, the computer still goes nuts and the phone goes, so never any privacy. And velocity squared there. Okay? Again, plug in the fundamental dimensions, all of that, and it'll have no net dimensions. Okay? Now, this is actually a bit like the Reynolds number. Okay, but you notice it's not in the same form. So what I'm going to do is, because it's dimensionless, I can invert this, so I can flip it around, exchange the numerator with the denominator of the fraction, and I'm also going to square root top and bottom. Again, we're square rooting a dimensionless number, so that's allowed. We're doing the same, we're always keeping it consistent. So I invert it, I've got b squared over gd, and then if I square root the top and the bottom, I end up with this, which is the standard form for Reynolds number in civil engineering. This is how we express it. Okay, so I've manipulated the group a little bit at the end to get it into a form that I know is a bit more manageable. So if I gave another engineer that equation, firstly they might say, why haven't you just given me the Reynolds number, because that's clearly what it is. It's a function of the Reynolds number. It's just in a weird form. But also if I give them that, they know exactly what it is. They know it's the Reynolds number. Okay, so that's dimensional analysis. So just follow the steps very carefully. Write out all of the parameters that are important in the problem. Write out their fundamental dimensions, and then use the n minus m approach. So you know how many groups you're arranging them into, and then for those groups, assign one variable that will only appear in one of the pi groups, and then the others will appear in all of them. Okay, and then we raise all of the repeating variables to an imaginary power, and then we write it out in this longer form, and then you equate each of the dimensions in the problem to 0. Just take care of this step. It's easy to rush it and miss ones. Okay, equate them all to 0. Work out the values of your exponents, and then from that you can plug them in here and generate a dimensionless group. So it's quite procedural. You just need to be a little bit careful at times so you don't make a mistake. But if you're careful, you always get the right answer. Sometimes at the end you might need to manipulate it a little bit. Okay, I'm going to give you one example now of choosing difference repeating variables. Okay, ones that are more difficult to measure, and I'll show you how. You'll still get a dimensionless group out, but the Buckingham PI is a lot more hard work. Right, so this time round I'm going to sort of invert the problem. I'm going to repeat these ones. Oh. I'm going to fix velocity and diameter. So I'll just go halfway through the Pi1 group and you'll see what I mean by choosing parameters. So to try and measure the dynamic viscosity of a fluid is not particularly easy. Far less easy than, for example, trying to work out a velocity or a length. And the same with the acceleration due to gravity. So now we've got rho, u, g. What I'll do it for first. And d. Okay, so we're going to raise these to powers a1, b1, c1. Write this out in full. So we have for our Pi1 group, we've got mass, length minus u, so density, a1, just check that's correct. Yeah. Length times minus 2 to C1, and then D, diameter is just length again. Okay? So now we're going to equate the dimensions again. So same process. So for length it's minus 3A1 minus B1, so length here, plus C1 plus 1. So same for time, minus B1 minus 2C1. And mass is A1 plus B1. And you can instantly see the problem is that we've got too many A, B's and C's in here. So we've got now to solve simultaneous equations. So it's just, in this case, it's slowed it right down. So you need to take a little bit more time now, working through and solving for the values of A1, B1 and C1. Okay, and you may well come out with, you'll come out with a dimensionless group if you do it properly, but it will be kind of less useful, probably more complex and involved than had you chosen easier repeating variables. So that's one of the ways it can be a bit complicated if you choose the wrong repeating variables. You'll still get a correct answer, it'll still be a dimensionless group, but it'll be slower to get there, and the group itself might be of a bit less use. Okay, but certainly your answer will still be dimensionless if you do it properly. Okay, so these three, definitely the wrong ones to repeat. But the first time round, like I say, with very little fuss, gave us a Reynolds number and the Reynolds number, which are two well-known dimensionless groups. Right, so that's Buckingham PI applied to a very simple problem.